Welcome. This lecture is called Spanning Sets. These um, sets are special in the sense that there are certain members of the set that play a substantial role in defining them. And the definition of a spanning set, the property actually of spanning particular sets, will continue to play a substantial role on other definitions and other concepts that we are going to study very soon. One of them is called the basis of a set or the basis of a vector space. But for now, we are going to immerse ourselves in this definition with some new notation. So the span of a set of vectors is the set of all possible linear combinations. So the short notation for describing linear combinations is a notation that involves this summation here. This operator here, this symbol denotes the sum of please bear with me if you are familiar with this, but if you are not, this sigma, this is a Greek letter, sigma denotes summation. That means that you're adding several terms, and what you're doing is that you're describing them using subindices as needed, so alpha sub I, u sub I, and then you're indicating that that I, index I, is taking values that are 1, 2, 3, 4, 5, 6, etc., until the letter P. That's the idea with this notation here. So I is an index. Here, maybe I is not the best choice for index, but it is an index denoting something that's switching values. In this particular case, I is not denoting the square root of -1. So it could be j, it could be k, it could be some other letter which changes in values. So the alphas denote scalars, which are in general assumed to be complex numbers. And so this summation is another way of describing what we denote as a linear combination. So in fact, you can, by reading the description of the so-called span, by reading that on the first description there, you have alpha 1 u1 added to alpha 2 u2, etc. There are p terms of this sum. Remember, each of those is a linear combination, so each of those looks like a scalar multiplying a column, scalar multiplying a column, and you have etc., until there are p of such scalar multiplications. So this entire summation is itself a column vector, right? And so there will be, or there should be right away, a similarity between the definition of a span and the formulation of the solution set of a system of linear equations, right? So the other thing to keep in mind here is the notation for span, okay, is going to make use this funky is something that looks like this. It almost looks like the symbol less than or strictly less than something, and then on the other side the symbol for greater than something, right? And so then you write something in between, and that thing that's in between, for example here, would be the name of the set. So the set itself is a collection of members, in this case p vectors, but putting these symbols around the name of the set is the set of all possible linear combinations, all possible. So that's considering all possible values of scalars. And that's what we agree on the definition. We agree on for using as a definition of the span of a given set of vectors. So here's an example. Consider a set that contains 5 column vectors, each of them with 4 entries. And now let's consider all possible linear combinations of, in other words, let's consider the span of S, okay? So even though we are considering the span, let's consider one member of the span. Okay, so each, in this definition, we are thinking that this would be U1, the next one would be U sub 2, this one would be U sub 3, this one would be U sub 4, and then the last one would be U sub 5. Okay, so but so U1 is the vector with entries 1, 1, 3, 1. Okay, so here's the vector 1, 1, 3, 1. So here is U sub 1, U sub 2, U sub 3, U sub 4, and U sub 5. And what we do now is to multiply each of those, right? So each member on this sum is something that looks like a scalar multiplication, right? So one of the, we're just making, it says here consider, so we're going to consider specific values for the scalars just for the purpose of illustration. So we evaluate alpha 1 at the value of 2, and then alpha 2 we evaluated at 1, and then the next scalar we're going to assume that is negative 1, and we evaluate 2, plug in 2 for alpha 3, and plug in the value of 3 for alpha 4 evaluated at 2, and then alpha 5 is assumed to take the value of 3. Then we carry out each of these scalar multiplications, and that would give us a column vector for each term in this linear combination. We add up entry by entry, location by location, and then we arrive at concluding that this vector here with entries -4, 2, 28, and 10 is indeed a vector that results from a specific choice of scalars that define this linear combination. And therefore, we would say that the vector W in this case is that vector of C4 with entries -4, 2, 28, and 10. That is W, and then we conclude that we say here that W is a member of the span of S. That's what this notation means. This notation saying that W belongs to the span of S is another way of saying that W is a member of the span of S. So we can learn more about the span of a given set by investigating which vectors are elements of the span. This, so to be, can I write here, to be or not to be or something like that. I guess, let me see, to be or not to be or not to be. Okay, so whether an element is a member or whether that element is not a member will be another way of translating the type of things we are used to address. Specifically, is this vector a member of the solution set of a linear system? Okay, so with that in mind, it's worth exploring whether or not a given vector belongs to the span of a set of vectors. So, for example, so here is a vector with entries -15, -6, 19, and 5, and we want to address is U a member of the span of S? So this is a question that we would like to provide an answer for. So we are asking, by asking this question, we're asking, are there values of scalars alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5 such that we can find the linear combination alpha 1 times the first vector, and then alpha 2 times the second vector. These are the elements of S, remember? So these are the elements. This vector here belongs to that set S, and so does this vector. That set S contains 5 vectors, right? So what we're exploring is that we can find scalars such that this linear combination is exactly equal to the candidate vector. This vector we are testing for membership. That's another way of expressing this. Is this a member or not? So this is a test of membership. So once we write this question as a linear combination, then we realize that, hey, turns out this type of question is no other than a question of finding values for the scalars, which is analogous, is equivalent to finding solutions for a system of linear equations. So we can form the augmented matrix and using the candidate vector here, we can use that as the vector of constants in the last column of the augmented matrix, and we can row reduce and proceed to calculate the solution set if there is any. So this is what we were talking about. So you can see here that in the last column of this matrix, we are storing that candidate. And so this augmented matrix has 2, 4, 6 columns, right? So here we have that n plus 1 equals 6. That would tell us that n equals 5. N is the number of scalars in this case. And then we compute the RREF. So that matrix, that augmented matrix, row reduces to this matrix. Immediately we see, okay, there are 3 non-zero rows. And since we know that n is 5, then n minus 3 would be different from 0. So there are no zeros on the last column of this RREF, and that tells us that indeed there are thinking on these problems, finding values for the alphas, for the scalars, is analogous to finding a solution set. This is the case in which the solution set contains infinitely many solutions, so we just need to identify which are the free variables, take some values for these free variables as scalars, and then compute the dependent variables in terms of those selected values, and then that's what will facilitate to come up with a particular choice of values for scalars. So if we wanted, we could do that, but this is enough evidence to say that U, based on our knowledge on solution sets, we can also argue that we have enough evidence to argue that U indeed belongs. It is possible to find scalars such that we can express U as a linear combination of the elements of S. And here's a particular example. Remember, there would be 2 free variables given by indices 3 and 5. If you evaluate them at specific values here for the sake of an example, we let alpha 3 be minus 2 and alpha 5 be equal to 2. And then the other values, alpha 1, alpha 2, and alpha 3 are the dependent variables, right? And then the relationship between free variables and dependent variables follows from the information that we have in the RREF. So using that information, we can find values for actually all scalars, and then we can verify that with those values, the linear combination is indeed exactly equal to the candidate vector that we're calling U in this time.